Welcome! In today's session, we'll explore the LeetCode problem number 1620, coordinate with maximum network quality. This problem challenges us to determine the optimal coordinate within a grid that maximizes network quality based on the positions and strengths of transmitters. Let's dive in and uncover the best approach to solve it. In this problem, we are working with an array called towers, where each element represents a cell tower with three properties: its x-coordinate, y-coordinate, and a quality factor. The signal quality received at any point, x, y, from a specific tower is determined by the formula q_i/1 plus distance, where distance is the Euclidean distance between the tower and the point, x, y. However, if the distance between the tower and the point exceeds a given radius, the tower's signal is considered out of range and does not contribute to the quality at that point. The goal is to find the point, x, y, with the highest total network quality, which is the sum of the signal qualities from all towers within range. If there are multiple such points, we are required to return the lexicographically smallest coordinate. Now, let's look at the input and output formats. The input includes the towers list, which specifies the coordinates and quality factors of the towers, and an integer radius, which determines the maximum range of influence for any tower. The output is a list, x, y, representing the coordinates of the point with the maximum network quality. To make this more concrete, consider an example where we have three towers located at 1, 2, 2, 1, and 3, 1, with quality factors 5, 7, and 9 respectively. If the radius is 2, the output is 2, 1. This means the point, 2, 1, has the highest total network quality when taking into account the contributions from all towers within range. Let's break down the reasoning behind the first example. At point 2, 1, we calculate the signal quality contributions from each tower. For the tower at 1, 2, with a quality factor of 5, the signal quality is 5/1 plus sqrt, 2, which is approximately 2.07. For the tower at 2, 1 itself, the quality is 7/1 plus 0, which equals 7. Finally, for the tower at 3, 1, with a quality factor of 9, the quality is 9/1 plus 1, which equals 4.5. Adding these up, the total network quality at 2, 1 is approximately 13.57. This is the highest quality among all valid points, which is why we return 2, 1 as the output. Now, let's examine the second example. Here, we have three towers located at 0, 0, 2, 2, and 3, 10, with quality factors 10, 5, and 12 respectively, and a radius of 5. At point 2, 2, the signal quality from the tower at 0, 0, is 10/1 plus sqrt, 8, which is approximately 3.54. The tower at 2, 2 contributes 5/1 plus 0, which equals 5. The tower at 3, 10 is outside the radius, so it contributes nothing. The total quality at 2, 2 is approximately 8.54, which is the highest among all valid points. Therefore, the output is 2, 2. Finally, let's discuss some additional considerations. The grid size is limited by the constraints, as all tower coordinates are within the range 0, 50. This means we only need to evaluate points within this range. It's also critical to handle numerical precision carefully, especially when calculating the Euclidean distance and the resulting signal quality, to avoid rounding errors. These constraints and edge cases ensure that the solution remains efficient and precise. For instance, if there is only one tower, and the radius covers its location, the output will likely be the tower's own coordinates. Also, if multiple points have the same quality, we must return the lexicographically smallest point to meet the problem requirements. To solve the problem of finding the coordinate with the maximum network quality, we first need to understand the underlying formula for signal quality. The quality contributed by a tower to a point is calculated as the floor of the tower's quality value divided by 1 plus the distance between the tower and the point, but only if this distance is within the tower's radius. This means the closer a point is to a tower, the higher the contribution to the network quality, provided the point lies within the tower's influence range. One basic approach to solving this problem is a brute force method. Here, we consider every possible coordinate within the smallest rectangle that encloses all the towers, which we call the bounding box. For each point inside this grid, we calculate the contribution from every tower. This ensures we explore all possibilities to find the optimal coordinate, but as we'll see, this can be computationally expensive. In the brute force method, after calculating the contribution from each tower to a specific point, we keep track of the point that gives the highest total network quality. However, this approach has a significant computational cost. If there are n towers and the grid size is determined by the side length L of the bounding box, then evaluating every grid point requires L² operations. For each point, we compute contributions from all n towers, leading to an overall time complexity of L² n. While this method is straightforward, it often evaluates points that add little or no value, making it inefficient for large grids. To address this, we can consider an optimized approach that reduces the number of points we evaluate by focusing only on regions influenced by the towers. In the optimized approach, we aim to avoid redundant calculations by limiting our search to a smaller region influenced by the towers. Instead of evaluating every point in the bounding box, we restrict our grid to the effective range of coverage, which is determined by the maximum radii of the towers. This ensures we only consider points where contributions from the towers are non-zero. Once the reduced grid is established, we calculate the total network quality for each point using the same logic as the brute force method. The point with the highest total quality is then returned. This method is much more efficient because the grid size is proportional to the tower's radii, reducing the computational cost to R²*n, whereas the side length of the reduced grid. However, the efficiency of this approach depends on the size of the tower radii, which can still result in a relatively large grid for high radius values. Another alternative is the coordinate sampling approach, where we test a smaller, strategic set of points instead of an entire grid. This method leverages the observation that the optimal coordinate is likely to be near a tower, as towers contribute the highest signal quality to nearby points. Here, we evaluate the network quality at each tower's location and its immediate neighbors. By calculating the total quality for this limited set of points, we can efficiently determine the best coordinate. This approach is particularly fast, with a time complexity of n², because we only evaluate a small subset of points. However, it comes with the trade-off of not guaranteeing the globally optimal solution, especially in cases where the best point lies far from any tower. This makes the sampling approach suitable for instances with a small number of towers and limited coverage areas. The optimized approach, which focuses on reducing the grid size and limiting calculations to the effective range of the towers, strikes the best balance between accuracy and efficiency. It avoids the brute force method's inefficiency by excluding points that contribute zero quality and provides better accuracy than the coordinate sampling approach. This method is particularly effective because the optimal point is guaranteed to lie within the bounding box of the tower's effective ranges, and there is no need to evaluate points far beyond these regions. While the reduced grid may still be large for towers with high radii, it is significantly smaller than the full bounding box. This balance between computational feasibility and accuracy makes the optimized approach a reliable choice for solving the problem, even for large inputs with many towers or wide coverage areas. To solve this problem, we need to determine the coordinate in a 2D grid that maximizes the total network quality generated by a set of towers. Each tower is defined by its position, x_i, y_i, and a quality factor q_i. The signal quality at any grid point, x, y, depends on the distance to the tower and the quality factor of the tower. Specifically, the quality is calculated using the formula floor, q_i/1 plus distance, but only if the distance is within the tower's signal radius. If the distance exceeds the radius, the contribution of that tower to the network quality at that point is zero. To optimize our approach, the first step is to define the grid bounds. These bounds are determined by the minimum and maximum x and y values among all towers, ensuring that we focus only on the relevant region containing potential optimal points. This gives us the range x_min, x_max for the x coordinates and y_min, y_max for the y coordinates, effectively limiting the size of the grid we need to evaluate. Once the grid bounds are established, the next step is to iterate through all integer coordinates within this range. For each coordinate, x, y, we calculate the total network quality contributed by all towers. To do this, we compute the Euclidean distance between the tower, x_i, y_i, and the current grid point, x, y, using the formula sqrt, x_i x, caret 2 plus, y_i y, caret 2. If this distance is less than or equal to the signal radius, the tower contributes to the total quality at x, y, based on the formula floor, q_i/1 plus distance. Otherwise, its contribution is 0. As we evaluate the quality for each grid point, we simultaneously track the highest network quality observed so far and the corresponding coordinate. To handle cases where multiple points have the same quality, we use lexicographical ordering to ensure that the smallest coordinate is selected as the optimal point. After iterating through all the grid points and calculating their respective network quality, the optimal coordinate that maximizes the total quality is returned as the result. Several key insights make this approach efficient and practical. First, by limiting our evaluation to integer coordinates within the defined grid bounds, we significantly reduce computational overhead while still covering all possible optimal points. Second, the signal contribution formula ensures realistic behavior, where the quality decreases with distance and becomes 0 outside the signal range. This aligns well with real-world scenarios. Additionally, we can leverage early pruning by skipping a tower's contribution altogether when the distance exceeds the radius, avoiding unnecessary calculations. These optimizations ensure that the algorithm remains efficient while delivering accurate results. The algorithm's implementation relies on simple yet effective data structures. Nested loops are used to systematically iterate through every integer coordinate within the grid bounds, ensuring comprehensive evaluation of the entire region. For tracking the maximum quality, we use basic variables to store the highest observed quality and the corresponding coordinate. This avoids unnecessary memory usage and keeps the algorithm lightweight. The tower data is stored as a list of tuples, x_i, y_i, q_i, making it easy to access and iterate over during the quality calculations. In terms of complexity, the algorithm iterates through all grid points, which is proportional to the grid size G, calculated as x_max x_min plus 1, asterisk, y_max y_min plus 1. For each grid point, we compute the contribution of n towers, resulting in an overall time complexity of O, G *n. This ensures that the algorithm scales well with the input size, as long as the grid bounds and number of towers are reasonable. Understanding edge cases is crucial to ensure the robustness of the algorithm. When there is only one tower, the optimal point will always be the tower's location, as it provides the maximum possible signal quality. For towers with non-overlapping signal ranges, the optimal point will fall within the range of the tower with the highest quality factor. In cases where multiple points yield the same maximum quality, the algorithm resolves ties by selecting the lexicographically smallest coordinate. Lastly, when the signal radius is very large, it's possible for all points in the grid to contribute to the network quality. In such scenarios, the algorithm efficiently evaluates the entire grid without missing any potential optimal points. By accounting for these edge cases, the solution remains consistent and reliable across a wide range of inputs. Here, we begin by importing the necessary functions from the math module, specifically floor and sqrt, which will help with rounding and calculating distances. Then, we define the solution class and the best coordinate method, which takes 3 inputs: the list of towers, the radius within which signal is received, and the grid boundaries. To identify the boundaries of the grid, we calculate the minimum and maximum x and y coordinates from the input towers. This helps us define the limits for where we need to search for the best coordinate. Next, we initialize 2 variables, best_quality to keep track of the highest signal quality encountered so far, and best_coordinate to record the associated coordinates. We then iterate over every possible coordinate within the grid, starting with the x values and, for each x, looping through all possible y values. For each coordinate pair, we calculate the total signal quality received from all towers. This is done by iterating over the list of towers and calculating the distance between the current coordinate and each tower's position. If this distance is within the given radius, the signal quality from that tower is added to the total. The quality contribution from each tower is calculated using the formula floor, q/1 plus distance, which accounts for the signal strength and its attenuation with distance. Now, once the total signal quality for a coordinate is computed, we compare it to the current best underscore quality. If the new quality is higher, or if the quality is equal but the new coordinate is lexicographically smaller, we update both best underscore quality and best underscore coordinate to reflect the new best result. The lexicographical comparison ensures that in cases where multiple coordinates achieve the same signal quality, the one with the smallest x value, and then the smallest y value, is chosen. After iterating through all possible coordinates within the grid, the function returns the best underscore coordinate, which represents the location with the maximum network quality. This approach systematically evaluates each point within the grid to ensure the optimal solution is found, making effective use of mathematical calculations and logical comparisons to determine the result. Here, we start by importing the necessary libraries and defining the solution class, which contains our main method, bestCoordinate. The goal of this method is to determine the coordinate within a given grid that has the maximum network quality. To begin, we initialize variables minx, max, min-y, and maxi to help determine the boundaries of the grid based on the positions of the towers. These boundaries will define the area we need to evaluate. We then loop through the towers array, which contains information about each tower's position and signal strength. For each tower, we update our boundary variables to ensure they cover all the tower coordinates. After determining the grid boundaries, we set up two variables, best quality to track the highest signal quality we've found so far and best coordinate to store the corresponding coordinate. Next, we iterate over every point within the range defined by our grid boundaries, systematically checking each coordinate to calculate its total signal quality from all towers. For each coordinate in the grid, we calculate the total signal quality by iterating over all towers. For each tower, we extract its x and y coordinates and its signal strength, q. We then compute the Euclidean distance between the tower and the current grid point using the distance formula. If the distance is within the given radius, the tower's contribution to the signal quality is calculated using the formula q/1 plus distance, and added to the total quality. After calculating the total quality for the current coordinate, we check if it is better than the current best quality. If it is, or if it matches the best quality but the current coordinate is lexicographically smaller, we update best quality and best coordinate accordingly. Finally, when all points have been evaluated, we return the best coordinate as the result. This implementation ensures that we find the optimal solution efficiently by limiting our search to the grid boundaries and carefully calculating the quality contributions. To solve the problem, we start by analyzing a simple case with a single tower. The input consists of one tower located at 1, 2, with a signal quality of 5 and a coverage radius of 2. First, we determine the grid boundaries by identifying the minimum and maximum x and y coordinates based on the tower's location. Here, the only tower is at 1, 2, so the grid to evaluate is limited to this single point. Next, we test the only coordinate within this grid, which is 1, 2. The distance from this point to the tower is 0, meaning it is directly at the tower's position. Using the quality formula, the contribution is 5 divided by 1 plus the distance, which equals 5. Since this is the only coordinate to evaluate, the total quality at 1, 2 is 5, making it the best coordinate. The final output for this example is 1, 2. Now, we consider a more complex case with multiple towers, where their coverage areas overlap. The input includes two towers, one at 0, 0, with a quality of 3, and another at 2, 2, with a quality of 4. The radius for both towers is 2. To determine the grid boundaries, we use the minimum and maximum x and y coordinates, which results in a grid spanning from 0, 0 to 2, 2. Starting with coordinate 0, 0, we calculate its distance to both towers. The distance to the first tower is 0, so its quality contribution is 3 divided by 1, which equals 3. The distance to the second tower is greater than the radius, so it contributes 0. The total quality at 0, 0 is 3, making it the best coordinate so far. Next, we evaluate coordinate 1, 1. For coordinate 1, 1, we calculate its distance to both towers. The distance to the first tower at 0, 0 is the square root of 2, resulting in a quality contribution of 3 divided by 1 plus the distance, which floors to 1. Similarly, the distance to the second tower at 2, 2 is also the square root of 2, and its quality contribution is 4 divided by 1 plus the distance, which floors to 2. Adding these contributions gives a total quality of 3, which is equal to the best quality so far, but the coordinate 0, 0 remains the best due to being evaluated first. Lastly, we test coordinate 2, 2. Here, the distance to the first tower is greater than the radius, so it contributes 0. The distance to the second tower is 0, resulting in a quality contribution of 4 divided by 1, which equals 4. This makes the total quality at 2, 2 equal to 4, updating it as the new best coordinate. The final output for this example is 2, 2. In the next example, we handle a scenario where there is a tie in the quality values. The input includes 2 towers, one at 0, 1, with a quality of 2, and another at 2, 1, also with a quality of 2. Both have a radius of 2. The grid boundaries are determined to span from 0, 1 to 2, 1, so we evaluate 3 coordinates 0, 1, 1, 1, and 2, 1. Starting with 0, 1, the distance to the first tower is 0, contributing 2 to the total quality. The distance to the second tower is 2, resulting in a contribution of 2 divided by 3, which floors to 0. The total quality at 0, 1 is 2, making it the best coordinate so far. For 1, 1, the distance to each tower is 1, contributing 1 from each tower, giving a total quality of 2. However, since 0, 1 is lexicographically smaller, it remains the best coordinate. Finally, for 2, 1, the distance to the second tower is 0, contributing 2, while the distance to the first tower is 2, contributing 0. The total quality is also 2, but again, 0, 1 is preferred due to being lexicographically smaller. The final output is 0, 1. When analyzing the time complexity of our solution, we start by looking at the individual components. First, calculating the grid boundaries involves determining the minimum and maximum x and y coordinates from the list of towers. This step takes n time, where n is the number of towers, as we simply iterate through the list to find these values. Next, we have the grid iteration. Here, we are iterating over a bounding grid defined by the minimum and maximum x and y coordinates. The total number of grid points is determined by the width and height of this grid, which we represent as m_x and m_y. The time complexity of this step is m_x*, m_y, as we visit each grid point once. Finally, for each grid point, we calculate the signal quality by iterating through all towers. Since there are n towers, this calculation takes n time per grid point. Combining these, the complexity of the signal quality calculation across all grid points is m_x*, m_y*n. When we combine the complexities from each step, the overall time complexity of the algorithm becomes n plus m_x*, m_y*n. However, the n term from the boundary calculation is negligible compared to the dominant term, which is m_x*, m_y*n. This tells us that the runtime primarily depends on the product of the grid dimensions and the number of towers. In scenarios where either the grid dimensions or the number of towers are large, the runtime will scale accordingly. Shifting to space complexity, the input towers are stored in memory, which requires n space. While iterating through the grid, we process one coordinate at a time without explicitly storing the entire grid, so this step requires only 1 additional space for temporary variables like total_quality and best_coordinate. Furthermore, no other data structures are used to store intermediate results, meaning no extra space is consumed. Summarizing the space complexity, it is n, primarily due to the storage of the input towers. When comparing this approach to a brute force method, the efficiency becomes even clearer. A naive solution would involve iterating over a large predefined grid without considering the bounds of the towers. This could mean processing an unnecessarily large number of grid points, significantly increasing the time complexity. In contrast, our algorithm focuses only on the minimum bounding box defined by the tower coordinates, keeping the grid dimensions practical and ensuring the time complexity remains m_x*, m_y*n. In terms of best and worst case scenarios, efficiency depends on the size of the radius and the resulting bounding grid dimensions. If the radius is small, the grid dimensions are compact, reducing the number of iterations. However, if the radius is large, the grid dimensions expand significantly, leading to more grid points and a greater computational cost. To summarize the complexities, the time complexity of the algorithm is O, m_x*m_y*n, and the space complexity is O, n. This makes the solution efficient for grids that are reasonably bounded and for scenarios with a moderate number of towers. However, as the grid dimensions or the number of towers grow excessively, performance could degrade. The algorithm strikes a balance between simplicity and efficiency, and its performance is well suited for typical problem constraints involving a manageable number of towers and grid dimensions. When working on this problem, there are a few common mistakes that can trip up even experienced coders. First, it's important not to overlook the grid boundaries. Many assume the search space is limited to the coordinates of the towers provided, but the optimal point could actually lie outside this range. Always ensure you're considering the full bounds of the problem. Another common error is using the wrong distance formula. The problem might specify Euclidean distance or Manhattan distance, and using the incorrect one can lead to completely invalid results. Pay close attention to what the prompt specifies. Additionally, ignoring floating point precision is another frequent issue. Calculations like divisions in network quality can lead to small but impactful inaccuracies if floating point arithmetic isn't handled carefully. Whenever possible, use integer arithmetic to keep calculations precise. Finally, brute force implementations can be inefficient, especially for large grids. Calculating network quality for every single grid point without optimization can lead to timeouts. To avoid this, focus on reducing unnecessary computations, such as skipping areas far from all towers where the signal strength is likely negligible. Now, another mistake to watch for is misinterpreting tie-breaking rules. If the problem specifies that ties for maximum quality should be broken by the smallest x coordinate and then the smallest y coordinate, failing to implement this correctly can lead to wrong answers. Double-check tie-breaking logic to ensure accuracy. From an interview perspective, this problem offers a lot of opportunities to showcase optimization skills. Discuss how you can narrow down the search space using properties like the inverse square law and the signal strength formula, which tells us the signal strength decreases sharply with distance. You can also explore greedy or heuristic approaches, such as prioritizing points near towers or within a limited radius. Be ready to explain how your solution handles edge cases, like scenarios with just one tower, extremely large grids, or ties in network quality. Additionally, you should be prepared to discuss the trade-offs between different approaches, for example, comparing a brute force grid search to bounding box optimizations or sorting towers by their signal strength. Each approach has its pros and cons, and understanding these trade-offs is key to demonstrating a thorough grasp of the problem. This problem is closely related to several other LeetCode problems that you might find helpful to review. For instance, LeetCode 149, Max Points on a Line, involves geometric calculations and optimizing brute force solutions, which aligns with some of the challenges here. Similarly, LeetCode 221, Maximal Square, focuses on grid-based calculations and dynamic programming, so it's another good problem to practice for building intuition with grids. LeetCode 296, Best Meeting Point, shares a striking similarity to this problem as it also involves finding an optimal point in a grid, but in that case, the goal is to minimize distance instead of maximizing a signal. Lastly, LeetCode 803, Bricks Falling When Hit, is another grid-based problem that tests your ability to handle efficient updates and calculations. Exploring these related problems can help you develop a stronger understanding of grid-based challenges and refine your problem-solving strategies. There are several alternative approaches to solving this problem, each with its own trade-offs. A brute force search involves calculating the network quality for every possible grid point. While this method is simple to implement, it's computationally expensive, especially for large grids, making it less ideal for time-sensitive scenarios. A more optimized approach is bounding box optimization, where you restrict the search space to a bounding box around the towers. This reduces unnecessary computations but requires careful implementation to ensure no optimal points are missed. Another approach involves using a priority queue or max heap to prioritize evaluating points based on their proximity to the towers. This can be faster for large grids but might be harder to code and debug during interviews. Finally, there's the discrete event simulation approach, where you focus only on specific points of interest, such as tower coordinates or intersections of influence regions. This is highly efficient but demands a strong understanding of geometric properties and edge cases. Each of these methods offers unique advantages, and the best choice often depends on the specific constraints and requirements of the problem. Great work! We've summarized the key points of the problem and the solution approach. Remember to practice similar grid-based optimization problems to strengthen your skills. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!